Hello, everyone. Um, Welcome to a talk in the Theory of Computation course. This is the first talk about streaming algorithms. But I will start by telling you a little bit about myself. So right now, I'm in the mathematics department in the Technion in Israel. Before that, I did my postdoc for 2 years in the Institute for Advanced Study. And before that, I did my PhD in the Weizmann Institute. My main interest, the thing I'm mostly interested in, is understanding how mathematics can help us understand and use computation in a better way. So this is how I think about computation, theory of computation. So this triangle represents mathematics. Mathematics has 3 components. The first component is definitions. Definitions are the way we define the framework. We lay down the axioms we want to work with. And this is the starting point of mathematics. After we explain everything formally, after we define the model, then we can make statements on the world we just defined. This is the second vertex, which is theorems. Then we can make claims about the world. And the last vertex in the triangle consists of proofs, which are ways to explain why the theorems are true. So this is a very brief and maybe high-level description of mathematics. And for me, the main thing that is interesting here in theory is that the connection between this very abstract internal world of ideas to the real world. So how can we use all of these mental constructs, these logical constructs, to understand the world better, to use it better? So this is the reason why I enjoy and why I try to follow this approach to science. So now I'm going to start discussing streaming, but I will start by explaining a slightly wider perspective, my perspective on a larger scale, on a higher level, and then we'll go to streaming. So the course is about the theory of computation. Inside this theory, there is the world of complexity, which I'm going to describe briefly next. And inside this world, there is the world of streaming algorithms, which is the topic of this lecture. And in this specific course, streaming, other than being interesting by itself, is a model that allows us to move relatively naturally from the model of finite automata, which is the thing you already discussed. And the model we really want to get to is the model of Turing machines. This will be done next. And streaming is a way to move from this world into this world, sort of a hybrid model between the two worlds. So this is one of the purposes of this model in this course. Before I will give some introduction to streaming, I want to give even more basic introduction to computational complexity. So the goal of this theory is to understand, using mathematics, how to use computational resources like time, the running time of an algorithm, the memory size of an algorithm, maybe the amount of randomness it uses, and any other computational resource you can think of. So this is the high-level goal of this theory. And the typical example of how you construct the theory is something like this. And so there is some computational goal we wish to achieve, some function we wish to compute, or maybe some functionality we want to have. And so this is the goal in the world. To do this, we have the current technology. So the theory is, here I call it devices. We have a family of functions, devices or objects. And examples that you saw is a device can be a finite automaton. Later, a device will be a Turing machine, and maybe a Boolean circuits, or maybe a communication protocol. So there are many ways to define what are the devices we are looking at. And the family of devices we choose has two components, has two properties. One is a device computes a function. Devices have functionalities. This is one aspect. The other aspect is with a device, we can associate a cost. The cost can be the size of the device, like the size of the finite automaton. It can be the running time. It can be the memory size. It can be various other things. So devices have functionalities and devices have costs. And now, what we really want to do is to have some functionality. The device is just a model for our technology. And so the real goal we have is to compute some function that we are interested in. And now, after we have we defined what are the devices we care about, we can define the complexity of a function. The complexity of a function is the minimum cost of a device that computes it. So devices have costs, functions have complexities, which is the minimum cost for computing it. And the goal of the theory, the high-level goal of the theory, is to understand this number. There is some function f that we care about, and then we want to understand what is its complexity. This is the goal of the theory. And this question has two aspects. One is proving that this number is not too large. This typically comes by finding an algorithm for solving this problem. This is called upper bounds. And the other is to show that this number cannot be too small, that it's impossible to compute this function too efficiently or with very low cost. And this is typically called lower bounds. So this is the main question in computational complexity theory, and it has two aspects. And today we are going to focus on a very specific family of devices, and this is the devices that correspond to streaming algorithms, or streaming in general. And so first, the model starts with a story. What is the story we want to capture, we want to model? So the story is that there is a stream of data. This means that there is a list of examples we see. So there is a data that arrives sequentially, one after the other. And there are many examples for such data. There is, you can think about it as a video or a camera feed. It can be the sound or a song. It can be the traffic of a computer network in some router. And it can also be the data that a machine learning algorithm gets, either while in the training process or in the real world where it interacts with reality. So this is the scenario we are interested in. This is the streaming scenario. And now the question that is we want to understand by defining a model and then trying to prove things about this model is what can we do in this scenario? What are our options? So one thing we can do with this data, if it's a video, we can just play the video, right? We can play the movie or the song, and this is sometimes enough. This does not, playing the video or the song does not require a lot of resources. We can also record the data. We can put it on the hard drive, but this starts to have cost. So maybe we cannot record it indefinitely. Another thing that we can do with this sequence of bits or images is to hide things in it and maybe to communicate to some other party, something that will be hard to detect. This is a third option that you can do. The fourth option I'm mentioning is maybe we can, in the specific objective we have in mind, maybe we can find a very clever way to manipulate the data to achieve our goal. So we want to find an algorithm. And maybe we can't do anything with it, with the current technology, or maybe with any technology. Maybe we can prove a lower bound, some impossibility result. So these are just some options that are available in this scenario. And in this lecture, what we're going to focus on is on the two last objectives, is discuss a little bit of algorithms, but mostly understanding how can we prove impossibility results in this framework. And keep in mind that this framework is a hybrid between finite automata that you already know and Turing machines that you will see later, and the underlying definition is more complicated. So this allows us to move from the two models. And I want to just summarize this talk. We will have two more talks in this lecture. So today I gave you a brief introduction or a high-level introduction to computational complexity theory. And then we saw a few examples or a few questions that come with a streaming scenario where the data arrives sequentially. The next lecture will be much more formal. We will see examples. We will define a model, a formal model, and prove some things on this model. And in the third talk, we will discuss a wider perspective, and it will be again less formal. So the next talk will be very formal, and the last talk will be again a bit of higher level. So I hope to see you in the next talk, and we will end this one. Hello, welcome to the second talk about streaming algorithms in the course about the theory of computation. This talk continues the previous talk. In the previous talk, we talked about computational complexity from a wide perspective, and then we gave streaming as an example that we will focus on. The streaming scenario is that a lot of data arrives sequentially, and our goal is to do something useful with it. And in the previous talk, we gave a few options to useful things we can do with it. And today we are going to define it more formally. But before a formal definition, I want to give a few examples that you can keep in mind when we provide abstract definitions. So there are three examples I want to discuss. The first, in the first example, you can think of the stream as the stream is a list of numbers, but you can think about it as the names of people that, let's say, go into a subway or something like that. And the question we want to answer after we saw some amount of people is how many people are there? How many different people are there? So in this specific example, there is 1, 6, 2. So these are 3 people, 5, 4 people, 18, and 3. So these are the names of the different people. And when I went over the stream, I needed to remember at every point in time, is the new element I just saw, is the new thing that arrived in the stream appeared previously or not? This is one thing I needed to know. And the other thing is, what is the total number so far? So there are 2 things I kept track of. And you can try to see if there is something non-trivial, some non-trivial algorithm here. You can try to imagine to see if you can think of a non-trivial thing you can do here. Okay, so this is one example. This is the number of distinct elements in the string. Okay. The second example is slightly maybe easier to solve. Here, the string again is a sequence of numbers, and we think of each number as a name of a website or address of a website. And the question we want to answer, for example, is what is the name of the element that appeared the most? What is the name of the website that was visited the most? So in this case, from a quick look, it looks like 7 is the most frequent. So it's maybe a little bit easier to solve, at least in the example when you look at it. And maybe later on you can think about ways to make this formal. In what sense this problem is easier than the previous? Maybe they are not. This is the second example, the most frequent element. And the third example is maybe slightly more elaborate. So here there is some graph. The graph, the vertices of the graphs are numbers, integers, and the stream of data is addition and deletion of edges, of connections between 2 vertices. And you can think about these operations as addition or deletion of edges inside a social network. So the graph represents a social network of friendships. And the stream is, there is a new friendship or there is a friendship that should be deleted. So let's say that this is the starting point of the the first graph we start with. And then the edge 1, 2 is added. So this is the first item is add the edge 1, 2. So this is the new graph after we add the edge 1, 2. Then there is the edge 1, 12 that should be added as well. So we add the new edge 1, 12. Then the edge 2, 4 should be deleted. So this is the edge 2, 4 being deleted. And then the edge 3, 6 should be added, but it's already here, so the graph does not change. So the social network is updated through time. And the question we want to answer is, inside this huge social network, what are the 10 vertices with highest degree? What are the 10 most connected users or members of the networks? So this is a slightly more elaborate story, but it's a very natural story. And you can ask many questions about a social network. This is just one example. Okay, so these are the examples, the 3 examples. And now you have them in your mind, so you can think about these examples when we talk about the formal definitions. So now we are going to define the model. Our goal in this computational model is to compute a function, f, and this function takes as input, this is a finite sequence of elements in X. So there is a set X, and X star is finite sequences of elements from X. And the function takes as input some finite sequence of elements and gives the output is in some domain Z. For example, the first example we saw is the function that assigns a sequence of elements, the number of distinct elements in this sequence. So this is one example of such a function. So a function of this sort, of this type, is the thing we want to compute. Our model will focus on one specific computational resource, the memory size, the size of the hard drive, or some other way to store information. And the way we will model it mathematically is we will have the memory, which is denoted by capital M, will be a string of bits of length m. So we will have m, little m, bits of memory. So this is the computational resource we want to focus on. So the goal is to compute a function of this sort, and the resource we want to model, to focus on, is the memory size. Now we need to define the device. What are the devices we are going to work with? So I remind you that the goal is to compute this function f. Now, the device we will call a streaming algorithm. What is a streaming algorithm? There are 3 components. There is the memory, which is some string of n bits. And then there are 2 functions, 2 procedures. One is an update rule. The update rule takes the memory at some time t, and the new data that arrives at time t, and produces the state of the memory after the data arrives. So this is an update rule for the memory. Okay, so this is one procedure in a streaming algorithm, is how to update the memory, the content of the memory. You can see the similarity here with the finite automaton of size 2 to the n. So the finite automaton also has such a definition where you move from some state and some input to a new state. So you already saw a similar definition. But a streaming algorithm also has a dictionary, a way to interpret the content of the memory and translate the content into a decision. So I call it a dictionary. It maps the state of a memory to an output. Yeah, the function we want to compute should output elements in Z. And the dictionary tells us if the state of the memory is M, then the output is D of M. Okay, so this is a streaming algorithm. This is the mathematical model for a streaming algorithm. There are three components. There is the state of the memory M and two functionalities, the update rule and the dictionary. And this integer M is called the memory size of A. So this is how we are going to call it. Okay, so this is a mathematical model. You can see that everything here is defined in terms of sets and functions, which is the way the most basic notions in mathematics. So this is the device we are focusing on. Now we are going to explain the functionality of devices. How does a device compute a function? Okay, so this is the next step we are doing now. So now the input to a device is a stream. A stream is a sequence of elements in X. So it's X1, X2, and so forth. And what does the device do? So let's write it down. So we have the stream X1, X2, X3, X4, and so forth. And at every point in time, there is the state of the memory. The state in the beginning is denoted by M0, which is assumed to be the all zero string. This is a string of length n. Then we take M0 and X1 and use U. So these two things generate M1 via the update rule U. So M0 and X1 generate the new state of the memory, M1. Then M1 and X2 generate M2, again using the update rule U, and so forth. So the device is actually this sequence of states of memory. This is what the device, the state of the device as time evolves. And what do we want the algorithm, what is the property of the algorithm we want to have in order to compute the target function f? We want the property that if we interpret the memory at time 2, we apply the dictionary on M of t, then the output of this interpretation is the value of the function we want to compute on the stream up to time t. So we can interpret M2 as the value of the function on the first two x's. We can interpret M10, and it will be equal to the value of the function on the first 10 elements. Okay, so this is the meaning of the streaming algorithm A computes a function f. So there are many quantifiers here, if you think about it formally, but the quantifiers just represent something natural. So there is a memory that is updated through time, and the algorithm succeeds in computing f if the memory tells us the answer. If the only thing we need to do in order to determine the value of f is to know the state of the memory. So this is the definition of a device computing the function. And now, as in the abstract computational complexity scenario, we can define the streaming complexity of a function. The streaming complexity of a function is the minimum memory size of a streaming algorithm that computes this function. So it is written here in words, and it is written here in a sort of a more formal language or notation. Okay, so now we have devices, or maybe before devices, we have functions, the thing we want to compute. Then we have a model, computational model, which is devices. And then we have complexity theory, which is for every function, we associate its computational complexity. And Now I want to move to a specific example that we will focus on to make this a bit more concrete. Before the example, I want to make 3 comments about the definition. So the first comment is that a string is an infinite sequence in this specific model, and the computation is defined on the entire stream, on the infinite sequence, but we check its correctness only at finite times. So this is one comment. There is an infinite object in the definition, and the definition of compute is actually only at finite times. We never check anything about infinity. So this is one comment. The second comment is that the model we just defined focuses on just one computational resource, which is the size of the memory. And the model captures this in 2 ways. First, the memory size is this parameter, this integer in the definition. And the 2 other functionalities in the device, the update rule and the dictionary, are just functions, abstract functions. And we don't care about their complexity or any other property. They're just abstract functions. So the only thing we care about in this model is this number, this parameter n. So this is the way we chose to implement the focus on memory size is by setting up all of these formal notions. So this is one way to formalize a model that is interested in memory size. And the third comment I want to mention, I will not speak about it in depth, is that in the model I just defined, there is no randomness. I did not use randomness for 2 reasons. One is that probability theory sometimes can be also abstract, and I don't want to add more abstraction at this point. And the second is that it also adds more quantifiers into the definition, and I wanted to keep the definitions as simple as possible. So these are the reasons I did not add randomness. But adding randomness to an algorithm is a powerful tool, powerful resource. And specifically for a streaming algorithm, it enables to do useful things efficiently. So just keep in mind that if you add randomness to your algorithm, maybe you can do better things. So these are the 3 comments. And now I want to move to the connection between streaming and finite automata. So again, I will be, this is a connection, streaming is a connection between finite automaton and Turing machines. So right now we are looking backwards. How does streaming relate to finite automata? So the goal of a streaming algorithm is to compute a function from finite sequences to some domain Z. And if this domain Z is the number 0 and 1, it is a Boolean function, then this function corresponds to a language. For example, the language of all the strings that are mapped to 1 via F. So a Boolean function and a language are the same things. And the claim or an observation, which I will leave you as an exercise to verify, is that if the streaming complexity of some function, some Boolean function f is m, so there is a streaming algorithm with memory size m, then the language that corresponds to m can be computed by a finite automaton of size 2 to the n. So the size of a finite automaton is exponential in the memory size of the streaming algorithm. And this is actually an equivalence between the 2 notions. So far, the streaming perspective and the finite automaton perspective is very similar, except that here we allow to compute non-Boolean functions. We did not just focus on languages, we allowed more abstract computations, more general computations. So this is the connection backwards to finite automata. And the goal of the theory of computational complexity is to understand the complexity of functions of interest. This is the general goal of computational complexity. So let's try to do this for a specific example. So through the example, I hope the example will help to understand the basic definition and to understand how can we compute this number or prove bounds on this number. The example we will focus on is a very simple example. It's a function that outputs 1 if the input is a palindrome and outputs 0 if the input is not a palindrome. So a palindrome is a string that when you reverse its order, it remains the same. So for example, the string 0, 1, 1, 0, 1, 1, 0, this is a palindrome. Or maybe I'll write it like this. The palindrome function on this string is 1, and the palindrome function on 0, 1, 1, 0, 1, 1, 1, this is 0. So this is the function we will focus on in this specific talk. And we will use this function as a way to understand computational complexity more generally. Okay, so before we go into the formal details, try to imagine what is the streaming algorithm you would use in order to compute this function. So imagine we have a sequence, an infinite sequence of bits. Yes, some arbitrary sequence of bits. And now you need to construct a streaming algorithm that reads the sequence. And at every point in time, the memory content allows to decide if the string we read so far is a palindrome. So here it's not a palindrome, not a palindrome, not a palindrome. It is a palindrome, not a palindrome, and so forth. So what do we need to keep in mind? What does the algorithm need to keep in its memory in order to decide this function, to compute this function? And the way we can make your thoughts into a theorem. So the theorem I want you to think about for a few seconds is, what is the streaming complexity of this function? This streaming complexity is the minimum integer, the minimum m that memory size m suffices to decide palindromes in a streaming way, a streaming model. So the answer to this question is that the memory size required is infinite. There is no streaming algorithm that can solve palindromes in the way we formally set up the model. And this is related or equivalent to the fact that palindromes as a language is not regular. There is no finite automaton that decides it, that computes it correctly. So this is equivalent. Okay, so somehow this is an unsatisfying answer. When a simple problem like palindromes immediately goes out of the computational model, somehow the model is not maybe interesting enough, or now it's a time to reconsider the definitions we chose. And this is what we're going to do next. So we are going to go back to the definitions. The reason we are doing this is that we got this very strong statement, but maybe it is too strong. It is not interesting enough. It is not accurate enough. It is not informative enough. So the way we are going to fix the definition is, instead of being interested in what happens for all times up to infinity, we are going to be interested in some finite time. We add some time capital T to the definition, and the streaming complexity up to time T is the minimum memory size we need to compute this function, but just up to time T. We don't care what happens after time T. So now we added the notion of time to the definition and to the notation. And now, in terms of the course, we added to the theory of finite automata the element of time. This element of time was not present in the definitions of finite automata. And from an algorithmic perspective, we can think about it as algorithms that can increase the memory size as time goes on. So this is a different perspective on this slight change in definition. So now we want algorithms that can, from time to time, add some bits to the memory. And now the main thing I want to prove today, it's a very simple proof, is that now for the function palindromes, we have the streaming complexity as a function of T. This function of T is up to constant linear in T. So the memory size that is required to answer palindrome up to time T is somewhere between T over 2 and T. This is the thing we are going to prove next. Okay. So the first thing we will do is to prove an upper bound. We will find an algorithm. This is a very simple algorithm. What is the algorithm with memory size T that can solve palindromes up to time T? So the algorithm is very simple. The algorithm memorizes the input. So I will not write this formally. You can, it may be a good exercise to define the update rule and the decision rule, the dictionary that underlies this very simple algorithm. It just memorizes all the input, all the data it sees, and then makes a decision. It's a very, the algorithm is maybe, doesn't do anything interesting with the data. So this is the upper bound. In this case, the algorithm is very simple. Now we're going to move to the lower bound. The lower bound is slightly more interesting, or it is more interesting. And the claim here is that if we want to compute palindromes up to time 2t, the memory size must be at least t. So up to time 2t, we need memory size at least t. And there are a few ways to view this. I'm going to use one perspective that I'm going to elaborate more on in the next lecture, the next talk. So here is how we are going to prove this. So think about the input at time 2t as consisting of x1, x2 up to xt, and then it will be more convenient to add new symbols y1, y2 up to yt. This is a string of length 2t. Okay, this is the input to a streaming algorithm up to time 2t. Now the first observation that allows to prove a lower bound. So first, maybe I'll use a different color. The memory state just at time t. We just care about the state of the memory at time t. There is some update rule, and we assume that this update rule allows to compute palindromes. So the memory state at time t just depends on x. X is the first half of the input. This is the first observation. This is because, in general, the memory the state of the memory at any time depends only on the input up to that time. You can prove this by induction, for example. The second property that is important for, so this is true for any streaming algorithm. Now, how does palindromes come into the picture? So the second property is that for every x, for every such x of length t, there is a unique y, again, of length t, such that palindromes on x and y is 1. For every prefix, for every left half, there is a unique right half that makes palindrome output 1. What is this y? Y is the reversal of x. This is the only string that will make palindromes output 1. Any other y will make palindrome output 0. Now, the conclusion from these two statements, so the third property we know, this is by definition, is that d of the memory at time t and y, so maybe it's not d. If we know the memory at time t and y, then we should be able to deduce palindrome of x and y. So this is, if the algorithm correctly computes palindromes, then the memory at time t and y should allow us to compute the value of the function, palindrome. And the conclusion from all of these three properties is that the map x goes to m of t, this map that is defined here, is injective, is 1-to-1. If this map is not 1-to-1, then two x's are mapped to the same state of the memory. But for each of them, there is a different y that palindromes accept. So it cannot be, if the 1, 2, and 3 hold, that this map is not 1-to-1. So I'm leaving, so you can write some more formal details if you want, but the intuition, I think, is clear. If two x's are mapped to the same state of the memory, then this state for one of the two y's will output the wrong answer. So this is the conclusion from these observations, and this means that m must be at least t, because there are 2 to the m x's, 2 to the t x's, and 2 to the m t's. So this is the conclusion from all of this. And so this is the lower bound about the streaming complexity of palindromes at time 2t. Okay, so the summary of all of this is that the streaming complexity of palindrome grows linearly in time. A corollary from this is that if we want an algorithm to work indefinitely for all times, then its memory size must be infinite. It cannot be finite. And the conclusion in terms of finite automata is that palindromes is not regular. And you can compare this line of thought we just discussed to the pumping lemma, for example, which is another way to prove that a language is not regular. Okay, so this is the discussion of palindromes, and I want to, before we conclude, add one more idea, a very central idea in computational complexity. And the idea is, now we prove that palindromes is hard. We prove the lower bounds for palindromes. This immediately implies that many other problems that are easier than palindromes, that are harder than palindromes, are also hard. So So this comes, the general name for this is reductions. We can reduce palindromes to some other problem. This reduction will show that the other problem is harder, because if we can solve, so let's do it, I'll write it. So we can reduce, we can take palindromes and we sort of can embed palindromes inside a different problem. We will see some example of the number of distinct elements. And this reduction will tell us that if palindromes, if this is hard, then this is hard. Or stated differently, if this is easy, then this is easy. Okay? So there is a lot of, or many types of reductions. You will see more complicated reductions later in the course. And you will see the importance of reductions when we will discuss computational classes. But I want to demonstrate it now for palindromes in a very simple example. So the example is that the streaming complexity at time t of palindromes cannot be larger, is at most the streaming complexity at time 2t for the number of distinct elements. So the number of distinct elements in the string is the number of distinct elements we saw, which is the side of this set. This is one way to define it. So palindromes is easier than the number of distinct elements according to this claim. And here is a sketch of the argument. So the way we will do it is we will take an input to palindromes and map it into an input to distinct. And this mapping will show that if we can solve distinct, we can solve also palindromes. So here is how we do this in this specific case. We take an input to palindromes of length t, and we map it to input to distinct of length 2t. So every element in W is a pair of an integer and a bit. So it is 1 x1, 2 x2, up to t xt. This is the first half of W. And the second half of W is t x1 up to 2 xt minus 1 up to 1 xt. So here the time is increasing, here the time is decreasing, and x appears in the same order. Here it is x1, x2 up to xt, x1, x2 up to xt. So this is the construction from x to W. And the observation behind this construction is that x is a palindrome if and only if the number of distinct elements in this string is t. So if x is a palindrome, then 1x1 is equal to 1xt. So this one and this one are the same, and this is true for all of them. So if x is a palindrome, the number of distinct things we see here is exactly t. If x is not a palindrome, then, for example, x1 is not xt. So the number will be larger than t. The number of distinct elements in W will be strictly larger than t. So this is a way to take an input for palindrome and make it into an input for distinct. And the conclusion from this embedding is functional. So if we can answer this question, we can answer this question. So we built a reduction from palindromes to distinct, and this shows that the streaming complexity of distinct is also linear in time. This is a conclusion from the lower bound we saw before. Okay, so let me summarize this lecture. So this lecture is about the streaming model, which is a hybrid model between finite automata and Turing machine. Streaming adds the element of time into the world of finite automata. And today we defined a model formally using sets and functions in mathematics. Then we focused on one specific example to try to understand the definitions. And we saw that the first take on the definitions was not informative enough. The answer was could be more meaningful. So we changed the model slightly. We added some more data to the definitions. And then we proved, the interesting part was to prove a lower bound in this framework. And the summary of this lower bound is that there is no free transfer of data. If you want to move some information from one place to some other place, you need to pay for it. This is maybe a summary of this intuition, the intuition behind the proof. And the second idea we saw is that we can reduce problems, computational problems. We can build reductions between problems. And this is useful because if we prove a lower bound for one problem, we can immediately deduce a lower bound for the other problem. So this is the two main ideas, main proofs we saw today. The next talk will talk about streaming, but from a wider perspective. And it will be, again, slightly less formal than this talk, where we gave formal definitions and we saw how to use the definitions in order to prove something. So I hope to see you in the next Hello, welcome to the third talk about streaming algorithms in the course on the theory of computation. In the previous two talks, we gave motivation for studying streaming. We described scenarios where streaming is natural, and we provided definitions for the computational model that is a way to formalize the scenario we want to understand, the streaming scenario. And then we proved some things in this model. We showed that palindromes, we understood the streaming complexity of palindromes as a function of time. And our main focus, the most complicated argument we saw was proving lower bounds on the streaming complexity of this function palindromes. And in the end of the second talk, we also discussed reductions, which is a very central tool, very powerful idea in computational complexity that can relate one problem to another problem. Today, I want to focus on streaming, but we're going to take a step back and try to abstract the scenario slightly. And we will talk about advantages and disadvantages of this abstraction. So today I want to talk about communication. And I'm going to focus on communication in the context of streaming, and maybe give you slightly more general perspective at the end of the talk. So communication and streaming. So this slide is an abstraction, a way to abstract the lower bound proof we saw. So in the lower bound proof, we took the input to the algorithm at time 2t, and we split it into two parts of equal length, x and y. X is the left half, and y is the right half. And the first observation we had is that the algorithm somehow, if the memory size is small, is somehow able to take x and compress all the relevant data on x to the memory. Okay, so let's do it pictorially. So the stream is x1, x2, up to xt. And then the stream continues as y1, y2, up to yt. And we think about it as being split into two parts. And the algorithm is somehow able to take all the data on x and move it into this side using m of t. So the message m of t, the memory content m of t, and the value of y should suffice to deduce the functionality we are interested in. This was this is a slight, this is just an idea or two ideas from the lower bound proof. So we think about the stream as the left part and the right part, and the algorithm is somehow able to compress the relevant information on X to the memory. And if there is no way to compress the data, then the memory should be high, large. The memory size should be large. So this is what we did in the lower bound proof. And we can now add some characters to the story and make it stand by itself. So the idea, the picture from above, can be abstracted as follows. The idea is that we can take a streaming algorithm and we can interpret it as a one-way communication protocol between two players. So we have the left part of the stream, x1, x2, up to xt. We have the right part of the stream, y1, y2, up to yt. And we imagine that the left part is in one room and the right part is in another room. And the left part is known to a player called Alice. And the right part is known to a player called Bob. And Alice does not know Y, and Bob does not know X. But Alice takes all the information she has, all of X, and translate it to a single message, M. And then she sends this M to Bob. So now Bob knows M and Y. And Alice sent Bob M bits of information, M bits. And now Bob should take M and Y, and from these two things, compute F of X and Y. So now we can think about it without the update rule. There is no update rule here. There is no element of time that is progressing throughout the algorithm. We fix time, and we take the update rule and just abstract it as a map from X to M. So this is where the update rule hides, but now we ignore it. We allow this decision to be much more powerful. M is not just an iterative application of some update rule. It is any function of X. So the algorithm now is much more powerful than a streaming algorithm. But now the situation is cleaner. It highlights key properties, and maybe these key properties are enough to deduce what we want to know. Okay, so the summary of this picture is that we can think of a streaming algorithm as a one-way. One-way means Alice just sends Bob a single message. So a one-way, two-player communication protocol for computing F, the same target. And this abstraction highlights, or can potentially highlight, important properties. And in the lower bound we saw, this abstraction was enough to prove a lower bound that was asymptotically sharp up to a factor of 2. This perspective has this reduction between streaming to communication complexity, to communication protocols, can be interpreted from the other perspective, from the hardness perspective. If we prove a lower bound on this communication model, we immediately get a lower bound in the streaming model. So this is an advantage of this reduction from streaming to communication complexity. But sometimes this abstraction comes with a cost. When we abstracted the model, we lost some of its details. So it is not true that every communication protocol is actually a streaming algorithm. This can be bad if the abstraction is not good enough. But in many cases, the communication perspective actually gives us the right answer. So this is one example where we have a model with many details, the streaming model, and we can ignore some of the details, move to a higher level, and this higher level allows us to focus on the important details. Maybe these higher levels will remove some important details. This we can know only after we think about it enough. The communication complexity perspective actually gives the right answer in many cases for streaming. I will talk about some other cases maybe where it is not strong enough later. The theory of communication is a theory that stands by itself. One-way communication was studied by Shannon where he started information theory, defining entropy, mutual information, and this is an extremely powerful and useful theory for understanding communication, but also in mathematics, physics, biology, making decisions. It's a very powerful tool. The communication perspective was also formalized by Yao and became a field by itself, and I will talk about this in a bit. And I want to say or advertise a book that Anup Rao and myself wrote about this topic, about communication and its role in computational complexity. So there are many applications of communication complexity inside computer science. So this is this slide is about two important theories that are related to communication and one reference to maybe study a little bit about these theories. And I want to give you an example of how communication complexity was used to prove a streaming lower bound. So here is a theorem. The theorem says that if there is a randomized streaming algorithm, so it's even more powerful than the ones we saw, and this algorithm does not even need to compute the number of distinct elements. It only needs to approximate the number of distinct elements, and the error can be square root of t. So it's a pretty big additive error. So if there is any randomized streaming algorithm that can just estimate the number of distinct elements, then the memory size must be linear in time. So this is a theorem. The way this theorem is proved, first, Indyk and Woodruff show the reduction from the gap Hamming problem to this problem. So they show that if you can solve some problem in communication complexity, if you can solve this streaming problem, then you can solve some problem in communication complexity. And the mechanism is similar to the mechanism we saw before. And then Chakrabarty and Regev proved the relevant lower bound in communication complexity. And I chose to mention this example because their proof is very geometric. It uses Euclidean geometry and Gaussian space. So somehow this seemingly simple streaming question leads to a very deep mathematical theory and structure, in this case in geometry. And later, their proof, Chakrabarty and Regev's proof, was maybe simplified in two works and also used ideas from different type of geometry, like Talleyrand's theorem, so from convex geometry. And recently, we also found a proof using Fourier analysis for this lower bound. So the story here is that the streaming algorithm, through the language of communication complexity, brings a lot of mathematics into the picture, which is a very powerful mechanism, a very strong way to understand the model. If there is all of mathematics below it that allows to prove things. Okay, so this is the example I wanted to talk about. And the last thing I want to say is that this perspective of communication that we saw today, that a streaming algorithm leads to a communication protocol, appears basically everywhere in computational complexity. So in distributed computing, where the parties are far away, there is a natural notion of communication. And also in data structure, where there is some place in the memory and you want to communicate with this memory, is also can be interpreted as a communication scenario naturally. So these are streaming, distributed computing, and data structures have natural communication interpretation. But the communication also appears in other models like Turing machines, like Boolean circuits, like branching programs, like proof complexity. So in many, many areas in computational complexity. And the main reason is that every computational device you can think of, somehow communication must be part of it. Some part of it should communicate information to some other part of it. So this is why communication is a useful perspective. And the last notion I mentioned is a slightly more geometric notion. So there is a way to extend computational complexity. The idea is that you can have a device has a cost, and then a cost and functionality, and then you can define computational complexity. This idea appears, can be abstracted for many scenarios, like the rank of a matrix. The rank of a matrix can be cast in this language. The rank of a matrix is the minimum number of rank 1 matrices that the matrix can be a sum of. So this is one way to define rank of a matrix. In the example I wrote here, there is extension complexity. Extension complexity is a property of a polytope, which is defined by, let's say, the convex hull of some finite number of vertices, or the intersection of half spaces. And polytopes can be also thought of as a computational devices, and operations between polytopes can be projections. And this leads to the theory of extension complexity. And it turns out that the ideas inside communication complexity are very important for extension complexity as well. So the summary of this slide is that this communication is a very central tool and source of questions in the theory of computation. And the last thing I want to do is summarize this lecture, the 3 talks. So these talks were about streaming, where we gave motivation and definitions and proved some things. And we mostly focused on lower bounds that were based on the idea that there is no free transfer of data. And this led us to think about communication, which is what we talked about today. And now going back to this course, now we are in the middle point between automata theory and the theory of Turing machines. So streaming is sort of in between the 2 models. And next you will understand how do you define a computer, Turing machine. And then you will try to prove properties about these, prove properties for these models. And as you will see, the model is more powerful, and proving things about the model become more complicated. So I hope you enjoyed the lecture about streaming, that it was clear. And if you have questions about it, please don't hesitate to send me an email. Good luck and see you later.